record in case we come to any brilliant realizations. Okay. So yeah, on WebAssign, the way, so what you're asking is, can it be set up to give feedback?
And under the settings, you can, but you
Mhm.
have it set so it's off.
Yeah. So we don't normally, yeah, let's look here. Let's go into um, the edit. We'll bring up lab 5. Edit. Yeah, I don't have like hints and things programmed in. So,
Right.
and the way I and a lot of the instructors do it, we don't want to tell the student whether they got it right or wrong ahead of time because then they'll tell the other students.
Yeah.
And so I think it's set up. Let's see, this has changed since I last looked at it, but it's here in the edit, right? For
It's edit
yeah,
settings.
yep, settings here. Yeah, so I have kind of a template set up. And but I think we can, if we want to adapt this, I think either you have the ability, or if not, I can change things on a
I
section by
I
section basis.
I tried to change the settings on my assignments only, but it wouldn't keep them.
Oh, okay.
So
Let's.
I was just wondering, I can understand, not wanting to give feedback to the other students. But it was also one where when I have students go through, they don't know which ones they got right or wrong. They submit and it gives them a score update, but it still doesn't tell them
It
which ones
should
they're missing the score on.
it should tell them after the due date.
Yeah,
Yeah, so after the due date, they should be able to see what they got right, what they got wrong,
yeah.
and what the answers are. Now, if you want them to see that information before the due date, we can make adjustments.
Yeah, I didn't want them to see the answers. I just wanted them because on other assignments that my other classes do that don't use this, it gives them a red X or a green check mark, and that's all it tells them.
And it will tell them that after the due date. But
Yeah.
so I'm on your section now. Let's see if I can make a permanent change. Um, Under settings here. So let's see, where would this be?
I think it's a kind of a ways down. There's kind of a matrix box that says that you can do a check this off and it will grade it this particular way.
Here in the edit
Yeah,
area?
I'm gonna bring mine up here.
Okay.
Um, but it
Advanced.
was one where it's under edit. The Just a second here, bringing it up real quick. I just barely got sat down just in time to get logged on here.
Hmm.
There were a couple accidents on the road, and
Oh,
so if I go to view assignment and I go to edit the assignment,
okay.
and then underneath that it's edit the settings.
I'm sorry. I thought I was sharing. I'm going to share, and then you can make sure I'm in the right place. Okay.
Uh,
I'm in
um,
edit. I'm on
so
lab
are
5 under edit.
you're in the edit,
Yeah.
and yours looks different than mine does.
Okay. Let me back out then.
So I just go under the view.
Okay.
So if you want to do the lab 5 view,
Okay.
and then up here on the top is edit assignment.
Oh, okay.
And then if you start scrolling down under settings, yeah, see, yours comes up different than mine.
Hmm.
Let me see if I can find what mine.
You go ahead and share yours. We'll see if we can figure this out.
Okay.
Oh, I got to enable 1 second.
Okay, see, so I'm in here, this one, and when I go to, I can back, I come down here and what I'm looking at is this right here, the correct, incorrect marking is off.
Right.
And
And
when I hit it, and then I try to save or do anything, it comes up, it won't allow me to change that.
yours looks like the old settings. I remember all that. So that's got to be here under the new settings as well. Where would that be? Learning tools and feedback. So scoring. Oh, let me, oh, click. Okay. Click on student feedback. Okay, so I'll share. Yeah, I think you have an option to update to the new, they redesigned the these pages anyway. So I was on scoring. If I come here to student feedback, uh,
Okay, so answer feedback, I see that. And you have yours only after the due date.
yes. And so I guess
It
that's
gives
this
you,
one here, always show.
yeah, that would probably do it.
Okay, let's see if it saves. Now, this is just on your section. Okay. And so what we could do is save this as a new template. And then it's a matter of switching all your assignments over to the new template, which I probably have to do on each individual one. Unless, so when you save that, it didn't save, did it? Probably because I created the section and made you an instructor. I thought I gave you the ability to modify, but maybe it doesn't let you modify this. But when you saved it, it put up a warning, some kind of
It just didn't, when I went back in, it wasn't there.
Hmm,
Like it went back to the original settings.
okay.
But I can look at that again and I could work with you later if you wanted.
I wonder if you can see that new template I made and select it. But anyway, yeah. Play with it just a little bit more. And if you can't get it to save, email me and I'll go through and for both of your sections, all your assignments, I'll switch it over to this new template that I created.
Okay.
And we'll try to come up with some way to streamline this in the future so I don't have to remember to do it every semester because I'll forget. And
So I went back in and it looks like it's in there now.
yeah, probably because I did it. And
Yeah.
another possibility is you can set up the course instead of me. Uh,
Uh-huh.
and then you would have this level of control. And some people do that themselves. They set up the course and add me as an instructor. So we'll figure it out.
Okay.
Yeah, and send me an email once you're ready. Once you give up, send me an
Yeah.
email so it's in my inbox, and then
Okay.
I'll know to do it.
Okay.
All right. Yeah, it's not my favorite system, but I'm still looking at an alternative that would be better. Looking for an alternative that would be better. And of course, then there's a huge migration issue. So I'm kind of stuck with
Yeah.
it for a little bit.
What I was finding is students were not sure if they did it right. And so then they were like, well, your score changed. What did you do? It seemed like it encouraged them more to go over and look at other people's work
Ah, okay.
than, hey, I did it right and I got good feedback. And so I'm going to keep going on it. And um, so I thought, well, I would try changing that and see if it made any difference in terms of people trying to gain a little bit more confidence in their work.
Yeah, what lab is coming up for you?
Um, in one class, I'm going to be doing the standard candle,
Okay.
and the other one, I'm doing the parallax lab.
So LNO1, are you doing standard candles next?
Yes.
Okay. And so the other one I can go to, this would be real easy now because I've created the template. I'll switch the parallax in the other, and you can see whether you like it. There's the concern that they'll submit something, they'll see the check or the cross, and if they got, the X, they'll just go and change it. And so
Yeah.
everyone's gonna ace it. Or they'll keep trying until they get a perfect score. So it changes the dynamic of it a lot.
Yeah.
But I'll just change your upcoming lab in each one, and you can tell me what you like. So
Okay.
feedback, always show, save. Yeah, I anticipate there could be issues. Yeah, where students.
Well, it seems like there's issues either way.
Yeah. The kind of the better thing would be not the check or the X, but maybe if we had coded some hints in. And I think that's what this help content's for.
Yeah.
Anyway, good
Okay.
open technical discussion. Okay, so moving on, we are doing lab 5 today. So let's take a look at lab 5. Is this right? Oh, this is your lab 5. 1 second. Okay, let's just start here at the beginning. So here are our videos through last week. Last week we finished lab 4. This week we're doing lab 5, and so these are the videos from last year. And here I'll go over the lab, I'll go over the background sections, I'll go over the procedure, how to do these things in Afterglow. But then I shot another video. I think this actually this other video is many years old now. I should probably reshoot it because the interface changed. It used to be that this lab we primarily did with sample data, and the sample data is perfect, and so it always works. Now that we've moved to this format where we encourage the instructors to collect fresh data every time, because the education research seems to indicate that the students have a greater sense of data ownership. If it's a fresh data set that the class collected at least, not every data set's pristine. So some of the issues that we encounter is, this is the R-Lyri observation. You're collecting 50 images, and some of those images may be on different telescopes. In the sample directory, they're all on the same telescope. They all have the same plate scale, the same pixel scale. But if you're mixing and matching different telescopes, they have different pixel scales. And so the photometry can be a little bit more subtle there. Like if you're doing aperture photometry and you're picking an aperture of 5 pixels, that can correspond to different apertures on different telescopes. And so your photometry becomes a little bit of apples and oranges. And so I shot this extra video showing how you can correct for that in Afterglow. The other issue is hot pixels. Some of these cameras have a lot of hot pixels, and if they land within the aperture, that can also lead to problems when you're doing your light curves and folded light curves. So there's some extra hints on how to deal with those cases. That's in this video here. And if we have time, I'll kind of run through the lab kind of quickly. Then if there's time at the end, I'll show you these kind of more advanced features on how to deal with heterogeneous data sets taken with different telescopes and how to get rid of those hot pixels if they prove problematic. And if I don't get to it, then I'll just copy this video over and you can see how it's done outside. Although Afterglow has changed a little bit, so you'd have to intuit where some of the controls have moved. Anyway, so that's kind of the plan. So lab 5, here's our assortment of videos at the top of the lab. We have, the 2-minute introduction, background. There are a number of background. There's a lot of background here because if you're going to do photometry, you're going to have to teach them the magnitude system. You're going to have to teach them photometry, how to calibrate photometry. And then there's some background sections on our standard candles. Physically, what are they? What is an R-Lyri? What is a Cepheid? What's a type 1A? So there's some background material to go through, and then overview of the procedure. And we have a lot of how-to videos on how to do this stuff. And so you see more videos than normal. Also, there's this really good video here that I didn't make, but my former postdoc, Aaron Clues, La Cluse, he just goes by Clues, who's now teaching faculty up at Central Michigan, explaining what period folding is. That's going to be part of this, right? You collect data on your variable star, but you're interrupted by the sun coming up or bad weather, so you get little bits of the pattern, and we have to kind of piece it all together to fill in the holes. And so we put some thought into explaining what period folding is. This video helps with that, and some changes we made to the graphing interface can help with that as well. Okay, so here's lab 5. So again, there are the links to the overview videos. In terms of the observing guide, I won't pull the guide up, but after lab 5 is lab 6. And there are observations for the students to put in. The instructor put in the observations for labs 4 and 5, for the reasons we talked about. 4, target of opportunity, and 5, it's a huge data set. But now it's back to the students putting in observations, and they'll put in observations for labs 6 and 7 and 9. 8 is a manual lab. So the lab 6 observations are very straightforward to do. It won't take them long to put them in. Just to back out so you see the flow of things, we're into the cosmic distance ladder. Lab 4 was parallax. That gets us out to like the middle of the galaxy, thanks to Gaia. Lab 6 is standard candles, and we use 3 standard candles, R-Lyraes, Cepheids, and type 1As to get farther and farther and farther out. R-Lyraes are good out to like the globular clusters, so Milky Way scales. Cepheids can get us out to nearby galaxies. Type 1As get us farther out. Okay, so they're going to learn the techniques in this lab. Lab 6 is an application lab of the R-Lyraes and the Cepheids. In lab 6, we do the Great Debate of 1920, the Shapley-Curtis debate. And so we use R-Lyraes to figure out the size of the Milky Way and our place in it, not at the center. We use Cepheids to figure out what were then called spiral nebulae. We now know that they're spiral galaxies just like our own, but kind of the prevailing thought back then is they were smaller things, and our Milky Way was the predominant object in the universe, and they were just smaller things out about us, like the globular clusters are. And so it's an application lab. They're going to apply the stuff they learn in this lab. This lab is more focused on the technique of measuring distances farther out, and then they're going to use it in the next lab to figure out our place in space, the next part of that story. So the observations for lab 6, let's look at those real quickly. Here, I just popped over to lab 6. I am sharing and I am recording, just double checking. Down here, observe spiral nebulae with Skynet, and then they'll show that they're galaxies. There are 5 spiral nebulae. Not all are necessarily observable at each time of the year, though I think most of them are, if not all, in the fall semester. And it's real simple. They're just going to put in 5 observations, single shot, 80-second high through exposures. So nothing fancy. Just remember to have them put those in so they have them ready for next week. Okay. Okay, back to lab 5. What else? We remind them here that we have questions in the background sections in this lab. Whenever we do, we point it out here at the top. Students like to just skip the background because they don't like to read and they don't like to listen to videos. They just want to get straight to the procedure and crank it out. So this is just a little warning. If you skip the background, you're going to lose some points. And of course, the reminder that's always there to go back and review the sources of error in the previous lab. By this point, your student population should be bimodal. Those who take this advice go back and learn from their mistakes, and those who don't, and they're still just making the same mistakes, saying human error, measurement error. Okay. All right, down into the sections here. Goals. I've kind of already laid this out. We're going to use R-Lyraes to get to Milky Way scales, Cepheids to get to nearby galaxies, and then type 1A supernovae to get to faraway galaxies. The R-Lyrae data set is fresh. You collect it as a class. The Cepheid and type 1A are archival. The Cepheid has to be archival because Yeah, there are Cepheids in the Milky Way, in the Magellanic Clouds we could use, but the idea is to get out to nearby galaxies. And at those distances, they're fainter. So we're limited, since our telescopes are small, we're limited to luminous Cepheids, and those tend to be long period. And so the one that we're going to do in this lab is a 60-day period. That's too long of a period for the students to collect the data. So that's archival. And the type 1A is also archival because you never know when they're going to go off. There are a number of supernova groups that use the prompt telescopes and the Skynet telescopes for various different things. And so this is drawn from, it's one of the type 1As they discover. And they discover supernovae every week or so using our telescopes. Again, that's another cool aspect of this whole curriculum for the students. They're using the same telescopes, the same interfaces that the pros are using to make big discoveries. And so they'll use one of these here. In a future version, I'd like to update it that they use like the most recent discovered, but yeah, we're not quite there yet. Okay, equipment's just the internet. So now on to the background sections. Magnitudes. So, and I apologize in advance, everything in the background sections, but I'll just run through it as you might with your students, but only faster. So, being astronomers, we measure things backwards and logarithmically. So it's a very non-intuitive brightness scale. Of course, it dates from the ancient Greeks who labeled the stars, 1 the brightest, 2 the next level, down to 5 or 6, where the human eye cuts out. And then we just kind of kept that scale or reintroduced it, formalized it, and there it is. So I don't use the term logarithmic with them because that can scare some of them, but I often refer to logarithmic scales as like powers of 10 scales. So it's a powers of 10 system that runs backwards. So large negative numbers are bright, such as the sun and the moon here, Venus at -4, Sirius -1, etc. Naked eye limit 6. With binoculars, you can get down to 10. Pluto there. Large telescope, visual limit, and then Hubble Space Telescope. And large Earth-based telescopes. Actually, Hubble got down to like 32 or 33. This is an old figure. I'm not even sure if we can put Webb on this because it may be an apples to oranges. Since they're in the infrared, it may not translate exactly. But anyway, that gives them an idea of what the magnitudes correspond to, but then how to measure them. And here's a little bit of terminology, and the terminology, of course, but they don't. Apparent magnitudes and absolute magnitudes. Or sometimes we just use the word magnitude by itself, and that by default is an apparent magnitude. So apparent magnitudes refer to brightnesses. They correspond to brightnesses, and the absolute magnitudes correspond to luminosities. And with these introductory students, don't go into the formal definition that absolute magnitude is the magnitude it would be if it was at 10 parsecs, or they don't know what a parsec is. So throughout the lab, wherever I say apparent magnitude, I almost always will write in parentheses, think brightness. And wherever I say absolute magnitude, I write think luminosity, just to always remind them what we mean by these astronomy specific terms. Okay, so here we're talking about how to measure an apparent magnitude of brightness. And unlike distance, which I like to say is the hardest thing in astronomy to measure, brightness is the easiest thing. But in this lab, and often you'll need the brightnesses to be calibrated. In this lab, we do need them to be calibrated to infer correct distances. And calibration is perhaps the most confusing thing for students. One calibration is always boring. Whether it's a physics experiment or astronomy or whatever, calibration is the most boring thing. And students may not fully appreciate why you need to calibrate. But you'll see if we don't calibrate, you totally get the wrong answer. And so here we walk them through an exercise. They're going to actually make a measurement and calibrate using a reference star. We walk them through this because later on in the lab, they'll do the same thing, but they'll do it in batch mode. They're going to have 50 images. They're not going to want to do this 50 times by hand. So we do it by hand here so they see what the procedure is. And then in the graphing tools and whatnot, we try to emphasize that we're using the same procedure, but they'll do it in a kind of a batch mode. So we get the uncalibrated magnitude. Let's say here's a finder chart. This is a Landolt field. Back in the day, the whole sky wasn't calibrated. And so if you want to calibrate something, you image your field, then you swing swing over to a Landolt field. And in that field, the stars are calibrated. And it was kind of messy because they may be taken at different air masses, et cetera. The APAS survey was the big revolution where the whole sky, at least for bright stars, got calibrated. And APAS South was actually carried out in one of the prompt domes in Chile. Anyway, so nowadays, anywhere you shoot in the sky, the brighter stars will have known values. And this is one of them. This is the reference star. So we're going to try to measure the brightness of this using this as a reference where we know the magnitude of that. That reference star has a known magnitude of 12.02. So let's pop over to Afterglow. Let me get rid of the data here. I was practicing for our Lyraes. Okay. Sample directory, Astro 101 Lab, standard candles. It's in this folder here, CD47. That's the name of the Landolt field. I can bring up the image. And finder charts are almost always inverted. So in the lab there, it's inverted. I think it's just because it's easier to circle things and write things on it if the background's white. Also, it could be because we used to print these things out and we didn't want to waste printer ink. So finding charts tend to be inverted. And you could do that in Afterglow. If you come up here to display settings, there's a inversion switch you can throw. And let's see, I'm supposed to be good at finder charts because I worked in the gamma ray burst game. And so the goal there was to find the point of light that's in your image that's not in the archival image. So looking at these here, yeah, that's my reference. And that right there is the star I'm going to try to measure. I don't have to, I can go back and check, but it looks oh, now I've scared myself. So I'm going to put them side by side. Supposed to be good at this. Yeah. Okay, yeah, there's that galaxy. There's that bright star. Yeah, so this is the reference, right? I thought I could do it without having them both on the screen at the same time. That right there is the star that I'm going to measure. Okay. Slide that back in there. All right, so we go to the light bulb. That's the photometry tab. And that's the star that we're measuring. And it put up, and well, let me click on the reference star as well. And so what we have is 12.85 and 11.12. You can see it's thrown up the aperture and an annulus. So this is aperture photometry. Okay, back to the lab here. And so they input the uncalibrated magnitude here and the uncalibrated reference star here. Then we tell them the reference star is actually 12.02. And so you take the difference, and that's a correction constant, and you can add that correction constant to anything else in the field that you photometer, and that will calibrate it. So you add that, the difference is 0.9, you add it to this, and you get 13.75, and that's the calibrated magnitude of star A. And you have to do this field to field because each image, if you don't calibrate, you'll come up with a different magnitude every time, just because changes in atmospheric transparency, etc. Okay. So a little practice on what magnitudes are and how to measure them and calibrate them. Then a background section on standard candles. And since there's a fair amount of background here, if you're doing a lecture course concurrently, some of this, and you have everything synchronized, some of this you can cover in lecture. So standard candles, this is about the relationship between brightness, luminosity, and distance. Again, distance is the hardest thing to measure. Brightness is the easiest thing to measure. Here's the 1/distance squared relationship that they probably are familiar with. And, if you know the luminosity, that's a big if you somehow know the luminosity and you measure the brightness, again, the easiest thing, you can solve for the distance and calculate it. Okay. But knowing the luminosity, you don't always know that. And that's where this is part of our bag of tricks. Parallax gets us so far out, and now we have these other tricks. We find objects that have special properties that clue us into the fact that, oh, this is this type of star or this type of explosion, and hence it has this known luminosity. And how do we know it has that luminosity? It's a kind of a bootstrapping process. And I try to emphasize this as we go through the lab. Take nearby stars that we measured distances with parallax. Well, okay, we have their distances then. We measure their brightnesses, calculate their luminosities. Then we realize, oh, all stars of this type, varying on less than a day, Aurillaris, they all have the same luminosity. Okay, great. Then we can use that. Farther out, we find stars that vary less than once a day. We know their luminosity, measure their brightness, flip it around, calculate their distance. And then we can use that to calibrate the next part of the cosmic distance ladder, like Cepheids, for example, though those are also calibrated to parallax. But then type 1As are calibrated to Cepheids. So it's a bootstrapping process. Again, calibration. And calibration is tricky for students to wrap their mind around. Anyway, another thing is students often will get confused between brightness and luminosity. And we ourselves often use the terms incorrectly. Like if something's really luminous, sometimes we'll say, yeah, that's a really bright object, when we really meant to say luminous. And so you may want to spend some time trying to drill that home. And a good example is a light bulb. Take a 60-watt light bulb, though nowadays they're probably more used to lumens. I'm still used to watts. Take a 60-watt light bulb. Doesn't matter how close or far away, it's always 60 watts. That's luminosity, it's intrinsic. The brightness depends on the distance. Okay. And then here's that same equation, the same distance equation, but written with apparent magnitude, brightness, little m, and absolute magnitude, luminosity, capital M. And I don't go through the derivation here, at least the survey. It's not a hard derivation, but at the survey level, I didn't think it was necessary. One thing I did notice early on, you may be looking at this equation saying, that doesn't look right. It's 10 to m minus m over 5. And it is. But we noticed that students made a lot of calculator errors with the fractional exponent. And so what we do now, the way we wrote it out here is we've just calculated the 10 to the 1/5 part. That's the 1.585, taking out that potential calculator mistake. Now, some will still mess up. Some will do 1.585 to the little m, enter, then minus big M, which of course gives the wrong result. But having the fraction in the exponent greatly increases the likelihood of student calculator errors we found. So that's why that looks a little different. Okay. Now, background sections. So that's how we calculate our distances. Background sections on the standard candles we're going to use. The first is the variable stars, the Aurillaris and the Cepheids. And these, they vary in brightness. That's why they're variable stars. To these students, I like to describe their atmospheres as stably unstable. These are stars in the instability strip on the HR diagram. Their outer layers oscillate. And when they're bigger, they're brighter. And smaller, they're fainter. And usually I leave it at that. If you want a deeper level of knowledge, what's going on is opacity changes. When it's in the compact configuration, the atmosphere is denser and the opacity is higher, so it traps energy more easily, builds up, which causes the outer layers to inflate. Density goes down, the opacity drops, and the light is released, and so then it lost that energy and it contracts. And then the cycle just repeats. So that it's an opacity effect that makes it happen along the instability strip in the HR diagram. And there are all sorts of variable stars. It's a whole zoology of them. And I don't know all of them and all their special properties. But here we simplified a lot for the students. If it's less than a day, we're talking about Aurillaris. If the period's longer than a day, we're talking about Cepheids. Okay. Talk a little bit about, again, that bootstrapping. What we did is we looked at nearby RLARIs where we could measure the distance with parallax, calculated the luminosity, realized, oh, they all have the same luminosity. So then we can use that for farther away ones. We measure their brightness, use the known luminosity, calculate the distance. And so here they are, all the same luminosity. And with the Cepheids, it's similar story. We found some nearby ones that we could measure their distance with parallax, calculate their luminosities, and they're not all the same, but we realized they're a function of the period. The longer the period, the more luminous it is. And these are the average, since they are variable, these are the average brightnesses, average luminosities. So there's a well-defined relationship there, and we have it written out here. So if you find a star and it's varying on a time scale of 20 days, then that's going to correspond to a luminosity of 10,000 solar, or -5 absolute magnitude. But here's the equation for it. Once you know the period, you can stick it in here. There is a log. We point out to base 10 so they don't hit the natural log. They don't need to really understand logarithms deeply. Just a button on their calculator that will give them the correct absolute magnitude. So with the Cepheids, you have a calculational step, unlike with the RLARIs. And then the last one, these are the type 1A supernovae. And there are, two types of supernovae, 1A and then type 2. Well, 1B, 1C, and the naming convention's terrible. 1B, 1C, and 2 are all the same thing. Those are massive stars where the core has become all iron and it can't support itself, and you have core collapse and it becomes like a neutron star, overcompresses, rebounds, maybe some neutrino pressure, blows up. So that's your typical type 2. The name, I don't go into this. With the students, I just call them 1 and 2, or 1A and 2. But just so massive star core collapse, that's a 2. If it lost its outer hydrogen layer due to strong winds and it has a strong helium content out there, we call those 1B. And if that layer stripped, we call them 1C. But the 1Bs and 1Cs are really like type 2s. The type 1As are a different beast completely. These are white dwarfs in binary systems. You have it's a close binary system. The other star, the white dwarf was the more massive star. It evolved first and became a white dwarf. And then this other one's evolving more slowly. It eventually gets to the giant stage. They're close, so you have mass transfer, and the mass goes over and increases. The simple story is, it increases the mass of the white dwarf to the Chandrasekhar mass, 1.4 solar masses, can't hold itself up anymore against gravity, begins to collapse, and it heats up. It's primarily carbon in there. You hit the carbon ignition temperature, here it is, 6 times 10 to the 8, and then boom, and the whole thing blows up. And that's why they're great standard candles, because they all go at 1.4 solar masses. As soon as you hit that, that's when it happens. So you're always blowing up the same amount of fuel. The type 2s are not very standard. Their luminosities are not standard, but the 1As are. Of course, that's a simplified picture too. That's a little bit more detailed just for you. Really, the mass streams over. You pile up a little bit on the surface of hydrogen, it compresses and it blows kind of every few decades. And that's just your standard nova. And it leaves helium residue. And so nova after nova after nova for thousands, millions of years, whatever it takes. Then the helium residue piles up to 1.4 solar masses and gives you the type 1A. So you get actually a bunch of little explosions and then a big one. Like that one we've been waiting for, TCRB. That was supposed to go off like a month ago, and now it's too close to the sun for us to observe. I was burning time on every Skynet telescope because, it could have gone off at any moment. So I was just imaging it constantly around the world, hoping to catch the beginning, but it didn't. It's late. It's not on schedule. It needs to learn some of our physics, I guess.
You know offhand when it comes back around?
I don't. I think it's going to be a couple months before we can easily observe it again. Yeah. If it still hasn't blown by then, great.
Yeah, it'll probably blow now that it's gone. So
yeah. Unfortunate. Okay, and so anyway, the difference between a 1 and a 2, and by that I mean really 1A and 2, with the 2s you get a plateau stage. Here's the light curve. The ejecta continues to burn. By burn, I mean fuse and release energy, and that keeps the light curve up high. And so by the shape of the light curve, you know what you have. If it peaks and comes down without plateauing, you have a 1A, and you can use that as a standard candle. And again, the calibration, we find these in galaxies that we've measured the distances to with Cepheids. And so we know the distance, measure the brightness, calculate the luminosity. We learned that they all have a luminosity of minus 19.3, which is also a simplification. In reality, that gets you close, but there is a peak delay correlation. So the people who do the cosmology and measure Hubble's constant, you really have to take in dark energy and all that. There's a little correction. So it's not a standard candle, it's a standardizable candle. But here in the lab, we keep it simple. We just say minus 19.3. And then you can find them farther out. Again, you know big M, you measure little m, calculate D. Okay. All good? Okay, let's do some of these. So here's where they put in the observation. We went through this before. We have the finder charts and all sorts of configurations because we're not sure exactly how the data will come back. You can click here to get a larger version that may help. And for each one, we give the Lyrae and a reference star, and we give the magnitude of the reference star, and I've corrected these for dust, Milky Way dust. Okay, and there's one for the fall, one for the spring, one for the summer. Now, the fall one, stupidly, and I need to update this, for my reference star, I picked a variable star. I made like the ultimate rookie mistake. But most of the time, it doesn't impact the analysis. But every now and then, it can make it a little bit harder to get the parity to the Lyrae. Next time I update this lab, I'll swap it over to this star right here, right next to it, of almost the same brightness. Yeah. Just so you're aware. Okay, and so they put in the observation. Then you have this very important question. Which one did you do? Because that sets the auto grading for the rest of it. If they get, it says 1 point, but if they get this one wrong, they're going to lose a lot of points moving on. Okay, and then it's repetitive, the good kind of reinforcing repetitive. They're going to do the Lyrae, then the Cepheid, and then the type 1A. Little twists for each. So let's do the glob, the Lyrae and the glob. I'll just go to Afterglow and do this. Let's get rid of this thing here. The fall one is 1261. I'll load this in. These were all taken on small 1K by 1K, so they load in pretty quick. And I was playing around ahead of time. But using the Finder chart, these are the ones. So here is the Lyrae. I'm down in the photometry part there. And here's the reference, which is a variable star. I'll use it. It works fine with the sample data. But if you're having problems, just switch to that. They're about the same brightness anyway. Okay, we clicked on it. It did the aperture photometry as we practiced before. And up here under sources, there's a little switch here. You can see I now have my 2 sources. And if I turn that switch on, it will find it automatically in every other image, as long as there's a WCS. So they don't have to click through on each image and look for it. There it is. This one's flipped around, but so that's great. So come back down here to photometry. Now that we have them, I'm just going to select all the images. Now, if you have other things open, you'll want to go and deselect those. Normally, before this kind of analysis, I clear everything out so I can just easily select all. And if that's open and you press the go button, it doesn't go, it just closes the box, just a word to the wise. But if it is closed, you can hit the batch photometry. At least when it's doing aperture photometry, it's pretty quick. Download it. And then you go to Astromancer. And we're going to use the variable tool. And I already have this data in here, but I'll load it once again. Open. And that which you just downloaded, you bring it in. And it'll probably look like this initially. The variable star was the fainter one here. So the blue one, that's labeled source one. So I'm going to select that as my variable. And what we're plotting here is the variable star magnitude plus the known magnitude of the reference star, which was written in the lab, 13.87. I already have it in here. But if you didn't have it in here, notice that that's what sets the Y scale. That's what calibrates. If I change it from 0 here to 13.87, then that calibrated all this here. And what it's doing is it's adding that correction constant, the true minus the measured for the reference star. If I go back here and split them here, you see the reference star, its brightness is changing depending on whether it's rising, setting, if there's clouds in the way. So that's why you have to do this on an image by image basis. And it just does it for you using this formula once you give it the true magnitude. So we see the thing varying, but there are big gaps, like when the sun was up or bad weather. And we want to piece this together. So next we go to the periodogram. And they don't have to understand periodograms deeply. This is a Lom-Scargill periodogram. It's like a fast Fourier transform. But for them, it's just a hint. You can set the range for our Lyraes. You want to go from 0.1 to 1. For the Cepheids, you want to go from like 1 to 100 days. So when we do the Cepheid, you do have to reset the range. But really, you just go to the highest point, put your cursor up there, and it's telling me about 0.33 is the period. And then we'll go to period folding. Now, let me reset this. Okay. And so I know the answer is going to be around 0.33, but it's really sensitive. Now, I could just go here to period and type in 0.33 and it's perfectly folded. But we learned the students don't have a great understanding of what's going on when we do that. So we spent some time thinking about this. Reset the form. With variable stars, you often plot two periods. Notice the same data twice. But to understand period folding, it's best to just have one period and then slowly lower the period. As things move up above the period you're testing, it gets wrapped around. So you can see those 2 points are about to move off and they're going to be wrapped around. So I'm just trying these lower and lower periods. And you got to be a little bit careful because there are false ones, like here around 0.94. There's something that kind of sort of works, but it's not the best solution. Yeah, I'll just skip ahead a little bit. If we go down to 0.9, I guess there's a little bit higher. Yeah, right around 0.99, it said there's something good. I think there's one false peak around like 0.5. Maybe I'll start up at 0.6. We're just wrapping it time after time after time, waiting for all the points to line up. So, there's a false solution there. It kind of works, but it's not great. It said 0.33 was the best solution. So let me go to like 0.4. And I'll inch my way down to it. And at this point, it's good to see two periods again. It really drives it home. So you can see it coming into phase there. And they can eyeball it, figuring out what works best. But here we have period folding. We can save the graph, print it out. Let's go back to the lab. I'm trying to move along at a good pace so we get it all. Okay, and so they'll upload it, and then they get their questions. What is the period? 0.3, okay. Is this consistent with being an R Lyrae? Yes, less than a day, so it's an R Lyrae. Okay, it's an R Lyrae. What's the average absolute magnitude? Think average luminosity. Back in the background section, we learned all R libraries have a capital M of 0.75. Okay, go to your graph and measure the halfway point. So halfway between the peak and the trough, it's right around here, 16.7. And if I didn't calibrate, that would be something totally nonsensical. That's why calibration is important. So 16.7 is the apparent that goes here. Calculate the distance using the equation. Now here it is again. Look up the true distance in kiloparsecs, percent error. They should be able to get it to a few percent. The biggest sources of error are difficulty estimating the average apparent magnitude halfway between the peak and the trough, because the peak can be fuzzy, the trough can be fuzzy, and you may have one bad photometry point. We don't in this one, but if you had one bad photometry point, it could ride above or below, and that can confuse students as to where the peak is. If there's time, I'll show you how to fix that. But measuring that middle value is a source of error. And also, all R libraries aren't exactly 0.75. There's some scatter. That's a source of error. I also include, but they're not really big sources of error, photometric technique, period determination technique, dust correction. Yeah, they're sources of error, but not significant ones compared to the other two. And sometimes they'll say, I picked the wrong star. That doesn't count. If you pick the wrong star, go back and pick the right star. If you pick the wrong star, you won't see variation. You'll see random, right? Because there's always some random. If you're sampling a constant star, there's some random noise, and it just gets stretched to fill the screen. And so if it just looks like random scatter, then you just picked a regular star. You didn't pick the variable star. Okay. This one I'll just describe, but skip in the interest of time. This is the Cepheid. And so again, as I said, it's a 60-day period, so it's archival. It's in a somewhat nearby galaxy. Here's the finder chart. Again, you can enlarge it. It's a little bit harder to see than the others. There's our reference. There's the Cepheid. And they go through the same procedure, and they'll end up with something shaped like this. They'll get that period of 60-some days. Is it consistent with being a Cepheid, longer than a day? So yes. And now they calculate capital M, because it's a function of the period with Cepheids. So they plug the period into the equation, calculate capital M. Again, measure the distance between the peak and the trough. Here it's about 17. And so that's little m, calculate the distance, look it up, percent error, should be a few percent. Same sources of error. Okay. Now I'll show this one because it's a little bit different. This is the supernova, type 1a supernova. And for this one, we don't give them the supernova. We say find the supernova. And let me show you how to do that. Delete these. Load in the supernova. One of these we have cleaned out the hot pixels and one we didn't. It's written in the lab. Hopefully I opened the right one. I did. Yeah. Okay. Did I not? Okay. So one of these points of light is the supernova. We give them a hint. It's close to the galaxy. Here's our reference star. And the way the pros do this is they do an image difference. And so we have them difference the first and the last image. Just by coincidence, they're at about the same level, so I don't have to change the levels to get a good subtraction. And so how do we do this here? First, we have to align them. So here's the aligner tool. I'm going to select the first and the last. And got to pick one as the reference. We're using WCS to align them. Submit. Okay, they're aligned. They're even cropped. And so then I'm going to go to Pixel Ops. And this is the default is image. So we select one of them. We're on 2 at the moment. We select 2 minus the last one. First one minus the last one. And let's not overwrite the file. Let's have it come up as its own separate file. We're going to submit. And here it is. Here's the difference. Okay. And these take a little bit of learning how to interpret. One thing I often do is I'll double click it to lock it in. And I'll load up this one as well. And I'll split the screen. And I can even sync their positions here. Okay. And so then you start looking. And as almost always happens when you do this image differencing, you get incomplete cancellations. They're a little bit misaligned. So you're looking for a point of light that doesn't have this black white and kind of close to the galaxy, I said. So if we zoom in close to the galaxy, there it is right there. There's the supernova. So we have the students mark it, label it, and they submit in, they screenshot that and they screenshot this and they submit those into the lab. Now, once they found it, we're going to do photometry. So let's go to this sources here. I'm going to clear out the previous ones. And we want supernova and we want the reference. And we'll come here and we want to do it for all of the images except for the difference. If they include the difference image, it will give a confusing data point. So we want to make sure they don't include that. I'm going to batch them, download it, upload it into the same tool. Even though it's the variable tool, we're not going to do any period folding here. We'll just use it. Let me set that back. I need to tell my programmer when we upload a new data set that we should reset that to none. So here's the reference burbling along. Here's the supernova. So source 1 is the supernova. Take the difference, and then in the lab, the reference star was 14.39. So 14.39. Everything is now calibrated. And it's clearly a 1A because it didn't plateau. What we want is the peak. The peak here is 14.56. So the same questions. Is it consistent with being a type 1A? Yes, no plateau. What's the peak? Absolute. That's in the background section. All 1As are minus 19.3. The peak that we measure, I think I said is about 14.6. Calculate the distance. So again, the good kind of repetition, reinforcing repetition. We don't have them try to look up the distance. This one, it's kind of hard to find. So we just give it 56,000 kiloparsecs, % error, same sources of error. Okay. I'll pause for a second. Questions, comments? I know I'm in my final couple of minutes, but for those who want, I'll probably go over a minute or two and show you how to do those corrections I mentioned for non-sample data, where you're mixing across different telescopes and where you have hot pixel problems. But I'll pause if there are any questions. This is good, solid, fundamental astronomy, right? Okay. Let's clear out these. I'll load in a data set that has the problems that I mentioned that you may find in your own data sets. Let's load in this one. This is the spring blob. I'll bring up the finder chart here to remind me which one it is or where the sources are. Yeah, I think I got it here. Okay. So I believe it's this one and this one. Let me just double check. Just a bunch in a row, a little triangle this, and then down over here. Bunch in a row. So this one and this one. I think this is the R. Lyrae. Yes, okay. So here's our Lyrae, and here's our reference star. I don't know why, I noticed this today, it offsets in the first one. I'm not sure why, but, okay. One problem is different plate scales. This is a mix of images from two telescopes with different plate scales. And the aperture here is a certain number of pixels. But even with the same telescope, maybe one night you had really bad seeing and things are blurred out. Or maybe it's windy. I think there's a good example of a windy one here. Yeah, see how everything's streaked a little bit? And here's circular apertures. So there are all sorts of things, bad weather, windy conditions can mess it up, different plate scales, different seeings. So we have a more advanced photometry setting you're welcome to try. Go up to settings, photometry, and switch from constant aperture to adaptive. And this will fix all these ills. See how it adapted to the streaked nature. The stars are streaked because the wind was pushing on the telescope. So this is now streaked. If you had bad seeing and the star is bigger, the aperture will get bigger. So it's kind of a nice fancy thing. So that's one way to make it a little bit better. If I come down to 42, I think this one shows the hot pixel problem. This camera has a lot of hot pixels. You see them all over the place. If you look at these apertures, they don't look right. They don't look like they're matching the star. And the reason why, I think it's this one here. Yeah. If I come up here to display settings and crank up the saturation level, there's a hot pixel right there in the aperture. Oh, here. And it's distorting the aperture. So if you're having hot, let me just actually run this. I'll select all, I'll run it. It'll be a little bit slower because of the adaptive aperture. I probably actually have this data set because I did it earlier. In the interest of time, I'll just. No, it's not it. I think it's probably this one. Yeah. .56. Isn't that amazing? I don't see any periodicity in here, but the periodigram very clearly says 0.56 is the period. Let me try that without messing around too much. 0.56. Yeah. And yeah, very nice, except this point is way off, and this one's also way off. Both of them, if you investigate, they have a hot pixel in the aperture that's screwing up the photometry. And the student may think this is the minimum and hence get the wrong average brightness. So if you do this, right, you collected the data for the class, you do the analysis ahead of time, you'll know if this is necessary. You can get rid of hot pixels. I'll go over here. Yeah, it is a little slow to do the adaptive, but even if you use the constant aperture, if you go here to, oh, just finished. If you go to show pixel operations, instead of image, I can go to kernel filter and I'll select everything else as an additional image. And it does a median 3x3 filter, and you want to overwrite. This will go through all the images, and for every 3x3 cluster, it'll find the median and replace the central value with the median. It's doing it now. Once it gets down to this particular one, reload, and see all the hot pixels disappeared? They're all gone. The whole thing's a little bit blurrier, so you do degrade the photometry a little bit, but it should all be better now in terms of, so the photometry will have a little bit more uncertainty, but it won't have that hot pixel problem. So if I rebatch this, again, it would take a little bit because I have it on the adaptive photometry. I don't need to, I could put it on constant, but I did this one as well. So let me just load it in the interest of time. I think it was this one. So now it's, hello cursor, there we go, 0.56 still, and see how it fixed that one and this one. So that's a way, and that stuff's not written up in the guide yet, in the lab yet, but you could do that median 3x3 filter, walk your students through it, get rid of any hot pixels if you notice it's a problem. And if it still looks like crap, then you may want to try that adaptive photometry, even though it's a little bit slower, because you may have a mixture of telescopes or observing conditions. It's just transitioning from using sample data that's perfect to real data. These are things we've learned you have to maybe think about. Okay, so I went 5 minutes over there. But those last two things can maybe save a disaster. You save this from disaster, depending on the nature of the data set. Any questions? All right. Well, next week we'll do the lab 6. That's the Great Debate of 1920, and that's a shorter lab. It's a little bit quicker. And maybe a little bit more fun. This is techniques heavy. Next one will be, you know, it's one of the greatest hits the past 400 years. It falls in that category. All right. Thank you very much, everyone.
Thank you, Dan.
Thanks, Dan.